Welcome to section 2.7, complex zeros of a quadratic function. All right, objective number 1. Find the complex zeros of a quadratic function. For a function f, the solutions of the equation f of x equals 0 are called the zeros of f. When working in the real number system, these zeros are called real zeros of f. When working in the complex number system, these zeros are called complex zeros of f. Okay? So, in our first example, we are to find the real zeros of each of the following quadratic functions, graph each function, and then label the intercepts. Okay? So to find the real zeros, the first thing that we're going to do is set all of our functions equal to 0 and solve for x. So in our first example here, f of x equals x squared minus 9, we're going to set f of x equal to 0, which means x squared minus 9 equals 0. And then we're going to solve for x. So we'll add 9 to both sides. Then we'll take the square root of both sides. Then we'll simplify. And we get that x equals plus or minus 3, which is a real 0. So this is a real 0. Okay? So when we substitute in a -3 or a 3 into our function, we will get 0 as our y. So that means our ordered pair is going to be 3, 0, and -3, 0. Now, when y is 0, or in other words, when x is 0, mind you, because we already said f of x equal to 0. When x is 0, so if we substitute in 0 for x, we would get -9 as our answer. So if we're trying to find f of 0, we would substitute in 0 for x, and we would get -9. Okay, so when x is 0, y is -9. Okay, and so those are 3 points that I'm going to now use to graph my function. So I have 3, 0, so 1, 2, 3, so that would be this point right here. And then -3, 0, so that would be this point right here. And then 0, -9, so that would be this point right here. Okay? And so now I can connect my dots, which makes a quadratic function called the parabola. All right, awesome. So we graphed the function. Now we need to label the intercepts. So the intercepts are going to be where the graph crosses the x and y axis. So I'm going to label that. So this is the label 0, -9. And then this is the point 3, 0. And this is the point -3, 0. All right. So I found the real zeros. I have graphed the function, and I've labeled the intercepts, which is exactly what our problem asks us to do. Okay? All right, let's do the next one. G of x equals x squared plus 4. So I'm going to set g of x equal to 0. Okay? That's going to allow me to find my zeros for this function. So that means x squared plus 4 equals 0. I'm now going to solve for x. So x squared equals negative 4. Okay. I'll take the square root of both sides, so plus or minus the square root of negative 4. And then I am going to simplify. So x will equal plus or minus 2i. Okay. So I know then that because I have complex, or sorry, an imaginary value, I know I'm going to have complex zeros. So I'm going to have complex zeros. In addition to that, I know there are going to be no x-intercepts, and there are going to be no real zeros. Okay. Alrighty, which means that I'm going to have to identify some other points to help me get an idea of what my graph is going to look like. So since we found our zeros for this problem, they're complex zeros, we can now set x equal to 0 to determine what the y would be. That will help us identify our y-intercept. So 0 squared is 4. So g of 0 equals 4. So we do have an ordered pair, 0, 4. This point right here, 0, 4. Now we need some other points. So we're going to need to substitute in some other values. So let's substitute in 2. So g of 2 equals 2 squared plus 4. So 2 squared is 4 plus 4, which equals 8. So g of 2 equals 8. And let's do negative 2 on the other side. So negative 2 squared plus 4. So that would be 4 plus 4, which also equals 8. So g of negative 2 equals 8. So my 3 ordered pairs are 0, 4, 2, 8, and negative 2, 8. Okay, so negative 2, 8. Get this point right here. And 2, 8. This point right here. And then I can connect my dots. Okay. And then label. So this would be 0, 4, 2, 8, negative 2, 8. All right. So from the previous example, we see that some quadratic functions have no real roots, and roots are just another way of saying zeros. Also notice that the graph in part B had no x-intercepts. However, the function in part B does have complex zeros. Previously, we've defined the imaginary unit I equals the square root of negative 1. Working in the complex number system, we can now restate the quadratic formula without restriction. So, in the complex number system, the solutions of the quadratic equation ax squared plus bx plus c equals 0, where a, b, and c are real numbers, and a does not equal 0, are given by the following formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay. So in these next examples, we are asked to find the complex zeros of each of the following quadratic functions, graph each function, and label the intercepts. Okay, but now we're going to use the quadratic function to help us. Okay. So we have f of x equals 2x plus x minus 4. So let's first identify what our a, b, and c are in our equation. So our a is going to be 2, our b is going to be 1, and c is going to be -4. Those are the coefficients in this function. So we're now entering this into our calculator, not into our calculator yet, into our formula. Let's first find the value in the square root. So the b squared minus 4ac. Okay, so b squared minus 4ac will equal b squared, which is 1 squared, minus 4 times 2 times -4. So that's 1. And then -4 times 2 times -4 is going to be a positive 32. So 1 plus 32 is going to equal 33. So when I substitute that into my quadratic equation, x equals -b plus or minus square root of b squared minus 4ac all over 2a. I now have -b, which is -1, plus or minus the square root of 33 divided by 2 times 2. And I can simplify this a little more. So I'll have -1 plus or minus the square root of 33 divided by 4. So I have two values of x. I have -1, x equals -1 plus the square root of 3 divided by 4. And I have x equals -1 minus the square root of 33 divided by 4. Okay, and we can get rough estimates of this value in our calculator. So let's do that. Okay, so in our calculator, we are going to create a fraction. So I'm going to go alpha and then the x here, and I'm going to press -1 plus the square root of 33 divided by 4. And then I'm going to do it again, but this time subtracting. So I'm going to set my fraction. So -1 minus the square root of 33 divided by 4. Okay. And I have my two values. I'm going to round to 2 decimal places. So the first one would be 1.19, and then the second one here would be -1.69. So let's write that together. Ooh, let's go back. Here we go. So this would equal again 1.19. Oh, it's approximate. So, and then this one would equal -1.69. Okay, so those would be considered my real zeros for my problem. Okay, they would be considered complex zeros due to the fact that it is a fraction. Oh, sorry, not a fraction, a decimal that is non-ending, so it continues on. All right. So next, what we're going to do is we are going to find our vertex. So the vertex is going to be the center of our quadratic. All right. So to find that, we are going to utilize the formula x equals, let me write this up here at the top for you. x equals negative b over 2a, and then y will equal f of negative b over 2a. And when we find the x and y, then we have found the vertex of our equation. So let's find that. So these are our zeros. These are our complex zeros. Okay. So then x, the x coordinate of our vertex is going to be negative b over 2a, which equals negative 1 over 2 times 2, which equals negative 1/4. So then the y coordinate would be f of negative 1/4, which would be 2 times 1/4 squared plus 1/4 minus 4. Okay. Now we can simplify this. So 2 times 1 over 16 plus 1/4 minus 4. Simplifying this some more, we'll get 1 over 8 plus 1/4 minus 4. Now you can definitely enter this into your calculator to help you get your value. And so this will approximately equal negative 4.13. So we have our vertex at negative 0.25, negative 4.13. That's going to be the vertex. Okay. All right, now let's estimate where these points are going to be. So for the first one, 1.19, that's going to be somewhere in here. And then negative 1.69, it's going to be somewhere around here. Then our vertex is going to be at negative 0.25 and then negative 4. So it's 2, 3, 4. So this is negative 4.13. So it's like right here. Okay. I also know too that if I substitute in 0 for x, I'll get negative 4. So I can plot that point. All right, so now let's connect our dots. And we just want a rough estimate of what this graph looks like. And I'm going to redo that. That does not look pretty. Hopefully yours looks better than mine. We're going to redo that. Okay, let's try this again. That left side just doesn't really look very curvy, but it's a little better. All right, okay, so now let's label. So we have 0 and negative 4. We have negative 1.69, 0, and 1.19, 0. And our vertex, which is right here, negative 0.25 and negative 0.13. All right, let's do another one. G of x equals x squared minus 2x plus 5. So our A equals 1, our B equals negative 2, and our C equals 5. So let's find our B squared minus 4AC. So that would be negative 2 squared minus 4 times 1 times 5. So that will equal 4 minus 20, which equals negative 16. Okay. So plugging that into the quadratic formula, negative b plus or minus the square root of b squared minus 4ac. all over 2a. So that's negative times negative 2 plus or minus the square root of negative 16 divided by 2 times 1. This will simplify to positive 2 actually, because a negative times a negative is a positive. Plus or minus the square root of 16 is 4. And since it's a negative, we're going to add I divided by 2. I can factor out a 2 in the numerator, so that's 2. No, it's not 2, it's a 1. If I factor out a 2, I'm dividing each term by 2. So 2 divided by 2 is 1, plus or minus 2i divided by 2. And then I will cancel out the 2's, which leaves me with I 1 plus or minus 2i. Okay. All right. So I have x equals 1 minus 2i and x equals 1 plus 2i. Those would be our complex zeros. Since they are complex, that means we have no x-intercepts. Okay, so we're going to have to plug in some points in order to graph this function. Okay, well, right off the bat, if I plug in 0 into this function, I'm going to get 5. So I know the point 0, 5 is on my graph. So that would be right here. So it goes 1, 2, 4, 6, 8. Yeah. All right. What else? Let's plug in some other numbers. So we can plug in 1. That's 1 squared minus 2 times 1 plus 5. So it's 1 minus 2 plus 5. And that equals 4. Okay. Then we can plug in 2. So 2 squared minus 2 times 2 plus 5. 4 minus 4 plus 5. So that will equal 5. Oh, so 2, 5, and 1, 4. Okay, so that means 1, 4 is our vertex. And we can check that by taking negative b over 2a. B is negative 2. A is 1. So that's 2 over 2, which equals 1. Find the y-coordinate. I'm going to substitute in 1 for f, which we just found to be 4. So our vertex is 1, 4. Oh, yay. That's so nice. Okay. So we have 3 points here. So we're just going to estimate our graph here. And it's going to look something. Ooh, I missed my dot. Let's try that. There we go. Much better. Okay. There we go. It's going to look something like that. So now let's label. So going to be 1, 4, 2, 5, and 0, 5. Beautiful. All right. So the discriminant, which is the b squared minus 4ac part of the quadratic equation, still allows us to determine the character of the solutions of a quadratic equation. So in the complex number system, we can consider a quadratic equation ax squared plus bx plus c equals 0 with real coefficients, meaning real numbers. So if b squared minus 4ac is greater than 0, then the equation has two unequal real solutions. If b squared minus 4ac equals 0, the equation has a repeated real solution, or a double root. If b squared minus 4ac is less than 0, then the equation has two complex solutions that are not real. So the complex solutions are conjugates of each other. So without solving any of these next quadratic equations, we need to determine the character of the solutions of each equation. So here we have a quadratic, x squared minus x plus 1. So we know from this quadratic that a equals 1, b equals -1, and c equals 1. So if we enter these values into the discriminant, we will get -1 squared minus 4 times 1 times 1. Simplifies to 1 minus 4, which equals -3. Since the discriminant equals -3 and -3 is less than 0, our solutions are two complex solutions that are not real and are conjugates of each other. Okay. So our solution is going to be two complex solutions. All right, let's do another one. -3x squared plus x plus 2 equals 0. So here a equals -3, b equals 1, c equals 2. The discriminant b squared minus 4ac is what we're trying to use to determine what type of solutions we're going to have. So let's substitute in our values. So we have 1 squared minus 4 times -3 times 2. Simplifying, we get 1 plus 24. 4 times 3 is 12. 12 times 2 is 24, which then equals 25. Now, 25 is greater than 0. So, since our discriminant is greater than 0, our solutions are two unequal real numbers. Alrighty. And for C, well, not A, well, there is an A, but it's an X. X squared minus 6x plus 9 equals 0. So A is 1, B is -6, C is 9. So our discriminant b squared minus 4ac, substitute in our values. So we'll have -6 squared minus 4 times 1 times 9. Then simplify. 36 minus 36 equals 0. Since our discriminant equals 0, our solution is a repeated real number. that is a double root. So this will help you in graphing and trying to find solutions to other complex equations. If you are able to look at your discriminant and determine right from the get-go what type of solutions you're going to have, you can eliminate and you can identify the values to work with to move forward in your process of analysis. So this is very, 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 very important. All right. Well, that concludes section on complex values, but this is section 2.7. All right. I'll see you in the next one.